Hello everyone. Today we're going to look at section 9.1 square roots, which is in chapter 9, radicals. A perfect square is an integer that is the product of an integer with itself. For example, 0, 1, 4, 9, 16, 25, 36, and I can keep going. The square root of a perfect square is the integer, or more accurately the integers, whose product with itself is the perfect square. Every non-zero perfect square has two square roots. The square roots of 4 are plus or minus 2, because both 2 squared and negative 2 squared are equal to 4. So again, the only exception to this is 0, because both positive and negative 0 are 0. So besides 0, every other perfect square has two square roots. The symbol, the square root, denotes the principal square root, which is the positive square root. So if you see that symbol, it means the positive square root. The square root is an example of a radical. What's inside the radical, so inside that square root symbol, is called the radicand. Radicals are also exponents, but we'll get into this more later. But it means that the same rules apply, and we'll see an example of this in a moment. So as an example, let's find the following. A, the square root of 144. B, negative square root of 9. C, the square root of 1/4. And D, the negative of the square root of 4 over 25. So for A, the answer is 12. So again, that symbol is the principal square root, so we're only concerned with the positive square root. And since 12 times 12 is 144, 12 is the square root of 144. For B, the answer is negative 3. So again, the square root of 9, we want the positive square root, which is 3, because 3 times 3 is 9. And then we want the negative of it, so the answer is negative 3. For C, we can use the fact that the radicals are exponents, and we can break it up. So the square root of 1 over 4 is the square root of 1 over the square root of 4. Now the square root of 1 is 1, and the square root of 4 is 2, so therefore we get 1 over 2. And again, you can try this out. Is 1 over 2 times 1 over 2 1 over 4? Yes, it is. For D, again, we can split up the radical sign across division. The square root of 4 over 25 is the square root of 4 over the square root of 25. And I forgot the negative sign in the middle, but that's okay. So it should have been negative root 4 over negative root 25. But either way, once we square root 4, we get 2. And square root 25, we get 5. So again, the answer is negative 2 over 5. Not all radicals are of perfect squares. And if it's not, what we can do is either try to simplify it, which we'll do in the next section, or just calculate it on a calculator. So we'll do that for now. So we're going to look at root 2 and root 28. Now 2 is not a perfect square. There is no integer. When you multiply it by itself, you get out 2. And the same goes for 28. So they are called imperfect squares, or just not perfect squares. And if I put root 2 into the calculator, I'll get out 1.4142136, blah, 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 blah. It's an irrational number. Same is true for root 28. If I put it into the calculator, I'll get 5.2915, and the numbers will go on forever. You can always double check this in your calculator by actually squaring out what you get and making sure that you do in fact get 2 and 28. You can also make sure that it makes sense to you. If you go back to A for a second, you look at root 2. Well, the perfect squares on either side of root of 2 are 1 and 4. 1 is the next smallest perfect square, and 4 is the next biggest perfect square. So that means that the square root of 2 should be between the square root of 1, which is 1, and the square root of 4, which is 2. So you know the answer should be between 1 and 2. You can do the same thing with root 28. 28 is between 25 and 36. So 25 and 36 are the perfect squares on either side of 28. And if we square root those, we'll get 5 and 6. So the square root of 28 should be between 5 and 6, which is what we get out. So you can always check to make sure you're on the right track, that you didn't hit any funky buttons on the calculator or anything. The next thing we're going to talk about just for a moment are higher order roots. So a higher order root is something that's bigger than the square root, something like the cubed root, the fourth root, the 10th root. So we're going to look at the cubed root for a moment. So to find something like the cubed root of 27, we're looking for a number, let's call it x, such that x cubed is 27, or x times x times x is 27. Now luckily for us, this is actually going to be a perfect cube, so there is an integer that when you multiply it by itself 2 other times, you'll get 27, which is in fact 3. So 3 times 3 times 3 is 27. To find this on a calculator, you could use the cubed root button if you have it on your calculator. Most scientific calculators don't. But I do have a button that looks like this. It has a little X inside the root button, and then usually something blank. So what you do is you type the 3 first, the 3 being the fact that we're looking for the cubed root of 27. So we type 3, then that little X root button, and then the radicand, your 27. And if you do that and then hit enter, you should get out 3. So let's try it on a couple other examples. A, what is the fourth root of 81? So what number times itself, times itself, times itself will give you 81? And B, the cubed root of 64. What number times itself will give you 64? So again, we can use this higher order root button on the calculator. So for A, you would be hitting the 4 first, then the X root button, and then the 81. And if you do that correctly, you should get out 3, because again, 3 times 3 times 3 times 3 is 81. If we do the same thing for B, hopefully you get out 4. So again, that's the same thing we have up here, except instead of the 27, you'll do 64. So that's how you do higher order roots in the calculator. So that's going to end at this section. So look over it, read through the book, make sure that you understand everything, and email me if you have any questions. Have a good night. Bye.